Right, hello, everyone. Welcome to this session about the best practices for half-bridge gate drivers for HEV EV. My name is Jonathan Cantor. I'm a product marketing engineer with the gate driver team at TI, and I will be the moderator for this session before I turn it over to Jackie. I just wanted to give a quick kind of rules of engagement here. You'll notice that in this WebEx session, all the participants are muted. So if you have any questions during the presentation, please use the chat feature. What I will do with those is if I can answer them quickly, I will do so. But if not, we will leave some time at the end to both go through questions that you all pose during the presentation, or we can also take extra questions through the chat as well. At the end that we can answer at that time verbally. But yes, thank you very much again for joining. Please use the chat function for all questions. And with that, I will turn it over to Jackie.
All right, thank you, Jonathan. Hi, everyone. Thank you for attending the high voltage seminar event and attending these sessions. My name is Jackie Hui. I'm system engineer in the high power driver team at TI. So again, this presentation is talking about the best practice for the half-bridge driver for EV and HEV. So let's get started. We will go over the agenda for today. As you all know, a half-bridge driver is commonly used in the automotive DC-DC applications, as well as using in the motor drive applications as well. And in the automotive environment, it can be a pretty noisy environment. And so the first portions of these presentations, I will focus on talking about the design considerations, like giving out some design tips on some of the challenges we commonly face when designing the half-bridge. The topic will include talking about the Bootstrap supply design, as well as giving out design tips and layout recommendations of how we can reduce the switch node noise, as well as improving the ground noise handling as well. I will also take this opportunity to introduce a new driver, UCC2792X. This driver, we apply a different architecture. So it has a different architecture than any of the traditional half-bridge driver. We have some test results as well as application example of how this new structure actually helped to address those common challenges that we face during the design. The second portion of these presentations, I will introduce an application circuit that actually will be able to transform the half-bridge driver to use as a high-side driver with 100% duty cycle. And this, you can find it for applications usage such as a battery disconnect or a DC circuit breaker. So let's get started with the Bootstrap circuit design. Before we go into talking about the component selections, I want to just give a little bit of time to go over the basic operations of the Bootstrap circuit first. As you know, the half-bridge driver consists of two drivers inside, a low side and a high side. With the high side driver being a floating driver, because its return path is at the switching node, we actually need to have using a floating supply in order to power it properly. So the Bootstrap circuit basically is the power supply for the high side driver. And as being a power supply, the boot cap is where we store the energy and supplying the driver or the high side driver when we need to turn on the high side FET. So that what it means is we have to find a way to charge up the boot cap, as well as have a way to discharge this boot cap to supply the power for the high side driver. The left two figure here basically show how the charging and discharging events apply during the Bootstrap circuit operations. The left top figure here, it shows that the charging event of the boot cap, basically when the low side is turned off, when we are doing switching operation between the high side and low side, when the low side is turned on and the high side is turned off, it creates a current path, which it allows current to flow from the power supply, which is the VDD pin in this example, to go into the boot cap and charge up the boot cap. The timing diagram on the right-hand side indicate by the blue box, the darker blue box, indicate how the voltage at the boot cap is rising up when the low side is turned on. Similarly, when the switch operation is reversed, when the high side is turned on and the low side is turned off, the energy stored in the cap will release, basically the charge will release to power the high side driver and in order to power the high side FET. This is also indicated in the timing diagram on the right, indicating with the lighter blue box in here. You can see that as the high side is turned on, the boot cap voltage is slowly depleting. This is because it's using its charge to keep the high side FET on. So as the cycle continues, as the high side and low side switching, this charging and discharging events continue as well. So this is the basic operations of the Bootstrap circuit. Now, after we talk about the basic operations of the Bootstrap circuit, let's go into each component and talk about how we can select the proper components for it. The Bootstrap circuit, it's pretty simple circuit. It has three components: the boot cap, the boot diode, and a limiting resistor, as shown in the figure in here. One most important component is the Bootstrap cap, because it's basically the energy storage unit to power for the high side driver. So this value we have to choose carefully. It cannot be too small, because if it's too small of a value, it may not be able to hold enough charge to power the high side MOSFET when it needs to be on. A small cap also leads to a potential high DVDT when it's charging up, which can potentially damage the HB pin in here, so which then it will damage the driver. The value of the boot cap cannot be too large either, because a larger cap takes longer time to charge. What that means is the applications need to keep a longer time for the low side to be on. It may not be applicable to some applications. And if the low side is not on for a long enough time, that means the boot cap with a larger value, it's not fully charged. And what it means is when we turn on the high side, it may not have enough or proper VGS value to keep the high side FET on properly. So it's pretty tricky. It cannot be too small of a value, or it cannot be too large of a value. So what's the right value to choose then? Well, our rule of thumb is to select a boot cap value that is at least 10 times of the MOSFET gate capacitance. There are more precise or more detailed calculations that we show on the screen in here. These equations basically take into account the duty cycle of the operations or of the applications. It also takes into account the quieting current of the driver, as well as the leakage current of the driver, and of course the gate capacitance of the MOSFET. It also look into the HB pin UVLO, because you do not want the boot cap to deplete below the UVLO threshold, because that will turn off the output. So if you follow these equations, it will basically help you to calculate what is the minimum value you should use for the bootstrap cap. Now, besides the value, there is other things that need to take into considerations here. Like for instance, the type of cap to use. We recommend to use low ESR, low ESL type of cap. We also recommend to choose a cap with temperature coefficient that is relatively stable. For example, using a X7R type of cap. The reason for that is over the temperature, the cap value will change. If it fall below its minimum value, then you go into the potential issue that is using a too small cap, which you will not be able to turn on the high side effect properly. And other things to take into account is the application switching frequency. Although the duty cycle is already accounted for when we are calculating the boot cap value, but if your applications is running at a high frequency, for example, like more than 1 megahertz, you might have high frequency noise coupling to the bootstrap circuit. In that case, you can consider adding a small cap in parallel with the boot cap, for instance, like a 100 nanofarad cap in parallel, to help filtering out the high frequency noise. Now, if your operation or application frequency is slow, like for example, in motor drive applications, now there's another thing you need to take into account, that is if you have additional loading that will take from the boot cap. For example, if you have a gate to source resistor that will increase the leakage current, that will be loading from the boot cap. So when you calculate the boot cap value, you should take that into account as well. Now, besides the bootstrap cap, and other cap that you also need to pay attention to is the VDD bypass cap. Because during the charging event of the boot cap, current actually, it's going to taking out from the bypass cap here, the VDD cap here initially. And what will happen is it will dip the voltage at the VDD pin. Because the VDD has a UVLO threshold, you do not want that voltage to fall below UVLO and ended up shutting down the output as well. So you want to use a large enough cap to hold this initial charging event, be able to supply the inrush current basically. For that, our recommendation is to use a 10x value of the boot cap value for the VDD cap. Okay. Moving to the next component. The next component is the bootstrap diode. So this diode is in place for the purpose to block the current going back to VDD when the boot cap is discharged, meaning when the high side is turning on. And for that, we will recommend to use a fast reverse recovery diode. The reason for that is if you look at the scope capture on the right-hand side here, the red box highlight or spot out the voltage or the raining that happened during the reverse recovery. You can see that it's a quite heavy raining that it can happen during the reverse recovery, and this raining can pose or increase the switch noise. And the understood that happening during this time, it may potentially also shut down the driver as well. So you want to limit the durations of this event. That's why we recommend to use a fast reverse recovery diode, or even consider using a Schottky. Another considerations when choosing the bootstrap cap is to select the right voltage rating and power rating for this bootstrap cap. The bootstrap diode. And the reason for that is you want to pick the voltage rating that is take into account the bus transients. Our recommendation is you choose the diode voltage rating that is similar to your MOSFET rating. So it will account for the V-bus transients as well. And in terms of power rating, our recommendations is to make sure the power rating is selected that the diode will be able to take on the peak current when the boot cap is initially charged. Now, besides picking the components or the rating for the boot diode, another thing to consider is the DVDT, which happened during the charging event of the Bootstrap diode. Too high of a DVDT can pose issue to the driver. For example, if you might observe undesirable pulses at the output, or a high DVDT can potentially damage the HEV pin as well. Because of that, we recommend to add a current limiting resistor in series of the diode. It can be a small, like 1 to 2 ohm resistor to just try limiting the peak current. Now, besides talking about like the component selections, when designing for a Bootstrap circuit, another one that designer need to take into account is the power supply or the bias supply startup sequence. The VDD pin or the HB pin, they are both supply bias to the driver, and they both have their UVLO threshold as well as UVLO delay time. So when the controller is start PWMing and providing the PWM input to the driver, you need to take into account the UVL threshold and the delay time. You do not want the controller to start inputting the input signal when the power supply is not ready yet. Otherwise, you may have issue of having a missing pulse on the output or a partial pulse on the output. Now, another one is when you are designing, when you're selecting the boot cap value, if a driver that has a relatively long UVL delay time, maybe in milliseconds, in that case, you want to make sure your boot cap value take into the account of the UVL delay, because you want to make sure the voltage at the boot cap when you charge up, it will hold to a decent value, not only for the durations of your high side driver on period, but also during the UVLO delay as well. So after we talk about the Bootstrap circuit design considerations, another common problem or common challenge we face during the half-bridge design is having switching node noise, especially with negative spike at the switching node. So what's causing the negative spike? Let's take a look at that. This picture shows the parasitic impedance. Parasitic element exists in any design pretty much. Most of those come from the layout. But what happened is if you see the red parasitic indicating here, this is part of the reasons why we are seeing a negative spike. So during switching, when the high side is turned off, the current continues to flow in the inductor. And at this time, the low side is turning on and current is increasing. This current mostly is going through the body diode for a short period of time. Now, this current combined with the parasitic inductance in here, it basically create a negative voltage with respect to the low side fed body diode. So this negative voltage is what you observe basically at the switching node. This can cause potential issue to the system. For example, it might cause driver malfunctions because this noise can couple to the ground and basically affecting the driver translation of the input signal. It may also cause bootstrap diode overcurrent. The negative pulse basically increase the inrush current going into the bootstrap cap when it's initially charging. And for the same reasons, it may potentially cause a overvoltage for the bootstrap diode as well, and this can potentially damage the driver. So what can we do to reduce this negative spike? As I mentioned earlier, most of the parasitic inductance is from the layout. So good layout is very, very important. The most basic or the most common best practice is to try to have a tight layout between the driver and your power transistor, like your power FET. Try to place your driver close to the FET as possible and reduce the chase link or the layout loop connecting to the power MOSFET. So this is the most basic best practice. But there are other challenges as well, and it is not uncommon to see the buck cap that sometimes it will place in a relatively long distance from the low side power FET. What that means is that will increase the parasitic inductance between the low side MOSFET gate, low side MOSFET source pin to the buck cap connections, which is the inductance in here. So with that, the increase of inductance, of course, it's making the negative spikes worse. So what can we do in this case? One recommendation we have is try to reduce this distance. So for example, you can consider adding a high voltage surface mount ceramic cap across the power FET. That way, it can reduce the distance and hence reduce the parasitic inductance between the low side MOSFET source pin to the buck cap distance and inductance, and therefore it can reduce the negative spikes at the switching node. Other things you can consider is using external components. As we mentioned, the negative spike can potentially cause over voltage at the bootstrap circuit. So one thing you can consider is to add a thinner diode between the HV pin and the HS pin to try protecting and avoiding over voltage and preventing over voltage of the bootstrap circuit. Another thing to consider, especially if you are using a driver that has a integrated diode inside for the boot diode inside, to reduce the noise at the switching node and reduce the slew rate at the switching node, you can consider adding a resistor, a small resistor at the switching node pin, the HS pin in here. What this resistor does is it reduces the current in the discharge path when the bootstrap circuit is discharging. So besides the switching node noise, ground noise is another common problem that we face when we are doing the half-bridge design. So this figure basically shows what happens and what's causing the ground noise. A lot of the design we have, it has a common ground between the system ground and the driver ground. Ideally, we want the current to flow from the MOSFET back to the system ground, which is back to the buck capacitors. And this is the ideal case. Unfortunately, the connections between the driver ground and the low side MOSFET, it does create a path that allows some current to flow through, and that's where the ground noise creep into the driver input, and it can potentially cause a mistranslations of the input signal, and that's having a undesired pulses on the output. So for this situation or this design challenge, there are a couple of things we can do to improve the performance. One is to add a small RC filter to the input pin. It can be just like a 100 ohm with 100 picofarad cap, like a small RC. Place it when you do the layout. Make sure you place the RC close to the pin, and make sure the ground, the filter cap ground has a good ground connection as well. This will help filter out this ground noise. And other options, which is going back to the layout, is to increase the impedance connecting between the controller ground and the powertrain or your system ground. This can be done again by carefully deciding how you want to partition your ground plane in your layout. For example, you want to separate, even though the design is a common ground design, you want to still have a separate ground plane, one for low current, for example, your controller ground and your driver input ground for low current ground, and other ground plane for your high current ground, which is your system ground. And when you connect these two grounds together, you can have a thin, narrow layout trace. And this way, basically, it will increase the impedance between the connections, and you will reduce the current or noise creeping in and going back to your input of your driver. There are other features that it's included in the driver to help mitigate this challenge, the ground noise. There are several features that we have in our driver. For example, the minimum input pulse rejections. The two driver example we show in here, UCC 27282 and UCC 27925, they are both have a minimum input pulse of 20 nanoseconds. What it means is if an input pulse is 20 nanoseconds or less, the driver will ignore it and it will not provide an output pulse for the output. Unless your input pulse is more than 20 nanoseconds, then the driver will translate that and create a corresponding output for it. Other features, other common features we have in our driver are interlock functions, as well as some of the driver has a dead time programmable pins as well to allow the system to program a different dead time. Both basically is to avoid the noise, the ground noise that is causing a unwanted pulse on the output and potentially causing a shoot through where both your high side and low side are turning on at the same time. And the third type of feature set, which is in our newer type of driver, is having good negative voltage transient support. This is to protect the driver to have any malfunctions or damage because of the ground noise. Like for example, UCC 27282 and 284, it has a switching node tolerance down to minus 14 volts with less than 100 nanoseconds. Its input pin also is able to support down to minus 5 volts. Our newest driver, which I will go into more detail later on, UCC 27925 and 928. These are the driver that I mentioned earlier at the beginning that has a different driver structure architecture. This one, not only we have a very high tolerance at the switching node, minus 200 volt, it also has a split input ground. So it separates out its input ground and the output ground with pretty much very small leakage. So you can consider they are two different separated, isolated ground inside the driver. But keep in mind, even though on this driver, the switching noise tolerance is pretty high from a negative voltage aspect, it doesn't mean that you want to have significant switching noise, even though the driver will not be damaged at the switching node. But this, again, remember the negative voltage can cause over voltage on your bootstrap circuit, so you still want to be able to limit your switching nodes even using this new type of driver. So that leads to our discussions of a half-bridge driver architecture versus the new architecture that I was mentioning earlier. So let's start with what a traditional half-bridge driver architecture looks like. So the picture here shows that this is most common half-bridge driver. The low side is powered by the VDD, which is the bias supplies of the driver, and the gate output basically is VDD, is what you're biasing it to. The high side is a floating driver, and it has a level shifter, and its gate output is basically VDD minus the boot diode forward voltage with respect to the HS pin. So this is what a traditional half-bridge driver looks like. And what I mean by the new architecture is what I showed on the right-hand side in here, UCC 2792X. So in this family, you can see the one big difference is both the high side and the low side, it has its own level shifter. So what it does is it basically improves the ground bounce immunity or the ground bounce performance, especially on the low side because it has its own level shifter. Another one I mentioned earlier is it has two ground. So one for the input side and one for the output side. It also has its own separate supply bias as well. So comparing to a traditional half-bridge driver, the bias, there's only one bias voltage bias supply pin. In this new architecture, we have three separate bias pin. So for the input, it is the VCC bias supply. You can simply connect it to your microcontroller or a power supply so they can share the same supply. And on the output, both the high side driver and the low side driver, it has its own supply pin as well as ground return or current return path. You can still, it doesn't mean that you need to have two separate supply to power this driver. You can still use a bootstrap circuit to power the high side and basically bootstrap it from VDD2 in here from the low side. But what it does is this architecture allowed this driver not only be used as a half bridge, but also be used as a dual high side or a dual low side. So I'll give some example later on in these presentations to explain how it's being used. So we talk about this new architecture. Now the question is, how does this new structure basically help to address our problem? And remember earlier we talked about basically three common challenge that we need to consider when we design a half bridge design, right? First one is the bootstrap design. How this new architecture help to ease up to make the bootstrap design easier. Another one is how can it improve the switching noise tolerance, and how about the ground bounce immunity? So let's look at one at a time. So starting with the Bootstrap supply design. If you remember earlier, we mentioned the Bootstrap, with the Bootstrap design, we have two challenges, right? We have a few challenges. One is we want to make sure that the DVDT at the high side supply bias, it's not too high, otherwise it might risk to damage the driver. Another one is you need to pay attention to the UVLO delay time. So what I show in here is a test setup. Basically, we want to test out how robust this driver or this structure is against a high DVDT during startup, as well as what is UVLO delayed, which then will affect how soon your system can start switching. So to run this test, basically we intentionally use a very, very small boot cap, which is 10 nanofarad, and we have a test circuit basically allowing a inrush charge current dump to this boot cap in a very short period of time. At the same time, we actually also start switching on one of the input. We start switching the moment that we start dumping the current to the boot cap. So basically, it's during the ramping up of VDD, we start switching as well, and we test how this driver react to this type of setup. So this here is the result of the test result. Channel 1 is the output signal. Basically, it follows what the input is. Remember, as I mentioned earlier, we start switching the moment we start charging up the boot cap. Channel 2 here, the blue color chase. Channel 2 here is what we show the voltage at the VDD. So a couple things I want to highlight in here. The first one is when we look at the zoom-in diagram or zoom-in capture here, you can see that with this setup, we are able to create a very, very high DVDT. It's about 1.3 volt per nanosecond. This device is specified with a max of 0.5 volt per nanosecond, so you can see how robust it is. With high DVDT, what it means is it allows you to have a little bit more flexible or easier to design when the choice of your boot cap, as well as more tolerance of inrush current and more robust in the Bootstrap circuit design. Another one I want to highlight is the VDD UVLO delay. So this driver actually we designed with a very short delay time, typical about 2 microseconds. My apology that I don't have a better zoom in here, but the red bar in here basically show the UVLO threshold in this device is about 4 volts. And you can see that the output is able to start switching following the VDD voltage in about less than 5 microseconds. So what it means is it also allows you to allow the system to start switching relatively quickly. And it also has one less worry when you design your boot cap, because you don't have to worry about including the boot cap value that needs to account for significant UVLO delay time. And then the next one I want to show is the switching noise handling. So we basically set up the driver in a way to push for very, very high switching noise. In this example, or in this test setup in here, we actually push it to about 300 volt peak to peak. And a note to you all, this driver is rated for 200 volts. So we basically push it beyond its apps max rating. And during this test, what we does is we keep the high side, we keep the PWM switching at the high side, but keep the low side input low. The reason for that is we want to look at if there is any missing pulse or undesirable pulses under this severe switching noise. So the capture here, the scope capture here, the green channel 4 is the switching node. You can see that the worst case noise is get up to almost like 320 volt peak to peak. And the blue channel here, which is channel 2, is the high side output. As I mentioned, we keep a PWM signal on the high side. So it's switching as what the input is and following the input. And the low side is we keep it low, and you can see that there's no undesirable pulses on the output. So the driver pretty much behaves as what it's supposed to, even it's under such a high switching noise. Assuming capturing here show that if we zoom into one of the peak noise at the switching node, the DVDT get to almost 180 volt per nanosecond, so it's a pretty high DVDT, and the driver is still operating robustly for that. And the last one I want to highlight is the split ground of this driver. So one example is motor drive in automotive. The motor drive design, for example, a belt start generator, they can suffer quite a bit of noise, ground bounce, and that can be a problem to a driver because it can affect its normal operations. And what this does is what this new architecture, again with the split ground, as I mentioned, the input and output ground has a tolerance of plus minus 200 volt with less than 10 nanoamp of leakage. So you can pretty much view it as an two isolated separate ground. So what that is, it allows you to really route your ground with a good layout, really separate your ground, your input signal ground and your system ground separately to reduce the impact of ground noise creeping back into the input of the driver. Other example for automotive usage is, for example, if your controller is put on the 12 volt side and your power fed on the 48 volt side. One example for that is when designing a 48 volt to 12 volt DC-DC. What the split ground allow is it allows you to have a very clean ground layout. You basically can connect the input ground to the 12 volt domain while the output ground is connecting to the 48 volt domain without the need of using a digital isolator, for instance. Another example to use is, as I mentioned, this driver not only can be a half-bridge driver, it can also be used as a dual low side or dual high side. So one example for unidirectional 48 volt to 12 volt DC-DC is if you are suffering, if your system is suffering a severe ground noise on the SR circuit or the SR driver here, you can consider using this driver as a dual low side because both channel has a level shifter, so we can consider it to use a dual low side to come back basically the ground noise and have the best ground noise immunity for your design. So that basically summarize what the common challenge or best practice we recommend when designing for a half-bridge driver. And moving on to the second portion of this presentation, it's to discuss how we can convert or transform a half-bridge driver to use for DC high side DC operations. The reason that we include this topic here is because we're getting different requests from customer asking if we can support 100% duty cycle with our half-bridge driver. And the reason for that is we are seeing customer that is looking to replace the mechanical relay with solid-state solution, for example, MOSFET solutions. And that is because, the mechanical relay has shorter, it has not as good as reliability comparing to power MOSFET, for instance. They suffer from wear out due to friction or oxidations. It has less cycle time comparing to solid state solutions. It also has slower reaction time. For example, to slower reaction time reacting to a short circuit event, for instance. So we are seeing, customer making such change. And with that change, they are looking to use a high side switch. And what is a high side switch in this case? A high side switch basically is a switch connecting between your bus voltage and the load. And the benefit of that versus using a low side is when the switch is open, your system load basically is pulled to ground. Instead, if you use a low side, that means when it's open, your system ground is floating, or your load is floating. It's what I mean. So that's why we are getting this request, and because of that, we come up with a simple circuit, basically using simple components to build an external charge pump, which can pair with pretty much any half-bridge driver, and you can use it for DC operation, and it can support 100% duty cycle. We will go into explaining how this circuit worked, but before we go into that, let's just take a look at what's required for this type of driver. As the automotive applications, the power rating of this type of application going higher and higher, that means a driver that need to support higher and higher current, or a MOSFET that need to support higher and higher current. Because of that, some of the integrated MOSFET and driver solutions may not be appropriate to use because it has a limitations of how much current it can support. And also because of the higher current requirement, we also see that there will be externally multiple MOSFET putting in parallel. What that means is a driver that not only need to support 100% duty cycle for DC operations, but it also need to have a strong drive strength because it need to, when you put multiple MOSFET in parallel, you need to be able to turn on and turn off with high gate charge with those MOSFET. And because of that, so as I mentioned, we come up with a simple circuit here. This circuit basically consists of two portions. One is a self-oscillating circuit, and another one is the charge pump. And the operation, the idea of the operation is pretty straightforward too. The self-oscillating circuit in here, using the low side portion of a half bridge, basically creating a PWM pulse, which then shifted this charge pump cap between the V-bus voltage and VDD. And in this process, it pushed the current stored in this charge pump cap to refresh the boot cap. We will go into how it operates in more detail on the next slide. So let's take a look at first how the self-oscillations signal is created. So it started with using the low side portion of the driver, and it starts with the LO, which is the low side output being off. So first of all, you will see there is this resistor divider and a cap. So the resistor here and a cap here basically form a RC and is connecting to VDD. So this becomes a current. When you start, it has a current charging up this RC cap and slowly increasing the Li, which is the low side input. And as the voltage increase above is VIH threshold. Excuse me. So as the voltage increase above the VIH threshold, the output turn on. And when the output turn on, what happens is it will then turn on this signal FET. And what this signal FET does is it creates a discharge path. So the moment this Li or the input charge up, you turn on the output, and the output then create a discharge path and slowly discharge the Li. Slowly discharge the Li and turn off the LO. So this cycle will repeat itself. This is what the signal looks like. The green indicating at the beginning when Li is charging up about is VIH threshold, and when that happens, the output turn on, and it will remain on until the low side output is fall below is VIL threshold, then it will turn off. So as this cycle repeat itself, so basically your output will have this square wave PWM output provided at the LO nodes. So once we have the self-oscillating signal, how does that work for the charge pump? Starting with when the when the low side output is high, what happens is it will push this charge pump cap up, its DC voltage up. So in another word, it will then push the current from this charge pump cap through this two diode and to the boot cap. And in this actions, basically it refresh the boot cap and keep the boot cap charged in order to keep the high side MOSFET on. Similarly, when the LO output is low, this charge pump cap is clamped with this diode in here back to the HS pin, which is your bus voltage. And it basically restoring charge back to this charge pump cap. So the charge pump cap basically has a DC voltage of about pretty much similar to the V bus, and its peak to peak voltage is between V bus and VDD minus 2 diode drop here. And this actions because the LO, it has a self-oscillating signal, and this basically is creating the action to periodically refreshing the boot cap and also restoring charge for its next cycle to refresh. At the same time, there is also a small current that is from the VDD going through the boot diode to refresh the boot cap as well, and the current will return through the low side. And this small current also helps to refresh the boot cap. With all this is how the circuit is maintaining a 100% duty cycle on the high side. So as I mentioned earlier, this Bootstrap, this external charge pump circuit pretty much work with any half-bridge driver you can pairing it with. However, keep in mind that because of the charge pump operation does require in some period of time that it will have both the high side and the low side turn on at the same time. This means you want to use a driver that is without an interlock. Otherwise, it will not work. Another one to also pay attention to is to choose a driver that has a sufficient VIH and VIL hysteresis, because the hysteresis is basically how long the on durations of the self-oscillating pulses. So here is 2 examples of driver that you can use for such operations or such applications. One is UCC 27284 and another one is UCC 27289. Now, we do have an alternative circuit in case you have to use a driver that has an interlock functions. And in this example here is a 600-volt driver on UCC 27712. This driver, because it has an interlock, so we cannot use the low-side driver portions for the self-oscillating circuit. Instead, the idea remains the same, but instead we will have to use a comparator basically to create, these voltage differences and hence creating the self-oscillation signal. So this basically wrap up our presentations for today. And in summary, we review the Bootstrap circuit design and its component selections. We also discuss what's the best layout practice we should do to reduce the switching noise and ground noise. We also introduce a new driver architecture, the UCC 2792X, and show some of the test results of how its robustness against switching noise as well as the ground bounce. And at the end, we also review an application circuit that can transform a half-bridge driver to a high-side DC operations with 100% duty cycle. So with that, I would like to thank you for your attendance for this session. And for the remaining time, we will open up for a Q&A. So you can input your question to the chat.
Yes, hey Jackie, we got a question from earlier in the presentation, specifically about selecting diodes in the Bootstrap. This is asking about high voltage. Example used would be like a 1000 volt V-bus. The question being, there are not very many high voltage fast recovery diodes in the market. Would it be possible to use multiple diodes in series to block 1000 volts, or what should we pay attention to at such a high voltage application?
Right, okay, thank you. So what we recommend is looking for, for high voltage applications, we will recommend to try to find a diode that has maybe a maximum of 50 nanoseconds for the reverse recovery. But if you have difficulty finding that, putting multiple diodes in parallel can be another option as well. Now, with that note, if your application is lower voltage, for example, 100 volt or 200 volt, you can pick a diode that is maybe typically like 30 nanoseconds. That will work as well.
Yeah, and I guess on that topic, kind of touched on it there. What is kind of the maximum reverse recovery time, or what is the reverse recovery time we should look for when choosing the boot diode?
Right. So for 100 to 200 volt type of applications, I would say look for about 30 nanoseconds. For higher voltage, like 600 volt or higher, you want to look for somewhere in like the 50 nanoseconds. That will be a good a good target to choose your diode. Okay, I see a question asking, what about isolated gate driver? So all what we talk about, those challenges here, the common practice or the best practice, it applies to isolated gate driver as well. It's just in general a good good design considerations for bridge driver design. And I also see another question, is there a driver port target for GaN, and what are the special considerations? We do have driver, I believe it's a single channel driver for GaN. I don't have a part number on top of my head. So Jonathan, if you remember, you can put it to the chat. But we do have GaN driver as well. Things to pay attention to is some of the the GaN FETs, they have pretty stringent like what your gate voltage should be. For example, typical 5 volt, and some of them, if you go beyond say 6 volt or hitting about 6 volt, you risk damaging the driver. So for example, the driver that I mentioned earlier, the UCC2792X driver, if you are able to maintain the bias voltage relatively stable at 5 volt, you can use it for GaN. Another question here, is there any consideration to use half bridge driver in full bridge applications? I would say the notes that we go over, it will apply to for full bridge design. A lot of our half bridge driver is actually used in a full bridge topology, and the same apply that you want to try to reduce your inductance to have good layout. The best thing is really to pay attention to your layout, because it pays off for a big time. I would say it's much easier than trying to find external components to try to work around the problem. Now, with that said, I would also recommend, if you do a new design, you want to have placeholder in your components. Like for example, even if you don't decide to use a gate resistor, do put a 0 ohm placeholder in there for your initial evaluations. Another one is put a, like for example, if your PCB has space, try to put a placeholder for a diode, like a Zener clamp at your switching node, because when you have your PCB, when you start your initial evaluations, if you have very severe switching noise, you might end up damaging the driver, and you will have a hard time to try to move forward in your evaluations. Now, if that happened, and frankly, it happened a lot of time, now what you can do is, because the PCB is already there, you cannot change your layout. What you can do is try to slow down your switching. That's what the gate resistor placeholder will help. You want to put even 1 to 2 ohm in place slow down your switching and at least get to not damaging the driver, and then start your debug process. And with that note, and other things that you can think about, you can consider during the debug is if you suspect that your Bootstrap circuit has problem and that's what's causing the issue, one debug approach is you can consider removing your Bootstrap component and actually power it with, say, a floating supply, for example, a battery. That way, you can see if you're still having a similar damage or similar issue. If not, then you know it's a component in your Bootstrap circuit, and you can start to isolate the problem. Okay, another question here is, does TI have single input, two output half-bridge driver with that time control? I believe we do have a single input, like single PWM input half-bridge driver. I am not sure if it has a configurable dead time control or not. My suggestion is to go to the TI website, the driver, the gate driver product page, and we have a very good search engine that you can search for.
Hey, Jackie, one other question. Going to the bridge, using the bridge as a high side switch, can the charge pump circuitry that you showed be shared among multiple high side drivers?
Okay, yeah, this is also a common question too. Basically, you can, but there are things that you need to consider. For example, your high side, when you have multiple high side, those high side connection has the same common source connections. Because if you want to share the charge pump, the circuit design is expecting with basically a common source connection. So if that's the case, then you can have a using like a single charge pump design and to supply for multiple high side driver connections. However, if the high side MOSFET connects to support different parallel paths, right, different parallel power paths, then its source pin voltage can be at different potentials. In that case, you cannot share the charge pump. There's another question here I missed earlier. The question is, do you recommend using tiny isolated DC-DC converter for high side. So I think the question is, do we recommend to use isolated gate driver for the high side instead of using a half bridge? I will say this is more of a design preference. As you can see, like our half bridge driver is pretty robust. So it's not necessarily to use a separate like isolated gate driver. But if there are other requirements in the system, for example, if there is a spacing requirement that a single half bridge driver cannot meet that, then you will need to use separate driver, like a low side driver and a high side driver. And for a high side driver, in our portfolio, you can consider using an isolated gate driver. In other scenario, maybe it's for the using in a isolated applications. In that case, we also see customer using, well, because it has isolation requirement. So customer use isolated gate driver for the high side, but for cost purposes, they actually use just a low side driver for the low side. So we've seen that too.
Looks like there's a new question. Do we recommend using our half bridge drivers in a phase shifted full bridge topology?
I would say yes, because it doesn't. So for the half bridge driver, the half bridge driver is pretty flexible, and again, it depends on your system noise, and as I show you in these presentations, our half bridge driver is pretty robust to ground noise. So I don't see a concern of using it in a phase shift, full bridge applications. Okay, I think we are about time. Oh, wait. Oh, we still have time. So if you have questions, feel free to put into the chat box. Oh, okay, a new question. Is it possible to get the recording of this event? Yes, I believe the recording will be put on the website when this event is finished. Okay, a new question. The question is, I don't see, so there is no half-bridge gate driver with more than 1,000-volt V-bus on the website, on our TI website. Are there any reasons we don't design such product and we have to use an isolated gate driver? The reason, so there are several things about, supporting, say, 1,000-volt. For one, that means for 1,000-volt V-bus, that means you need to have over 1,000-volt tolerance on the driver, and there is challenge on doing it with like a traditional half-bridge or high voltage gate driver in terms of the process limitations. So for that, in order to support that, the architecture of the driver needs to be different in order to support such a high, voltage, as well as its peak current. Peak voltage and transients, and that's why it falls into the isolated gate driver aspect of it. But I also want to bring up, like, with that said, as I showed you earlier during the presentation, the new architecture for, as a half-bridge driver, this architecture actually opened up for us to support higher voltage half-bridge, but it's still a challenge in terms of 1,000-volt, but we do have plan in our future to utilize this new architecture and support higher voltage than, say, 600-volt. All right, I don't see any new question coming in. So I want to thank you for your attending, and I think we can close this section.